Hello everyone, my name is Devashish Lohani and today I'm going to present to you our recent work on spatio-temporal convolutional autoencoders for parameter intrusion detection. Here is a brief outline of this presentation. I will introduce you to the objectives of this work, followed by some major existing works, then our used approach, followed by the datasets we work on, and finally our obtained results and conclusion. We have two objectives in this work. Our first objective is to reproduce results of the default framework. In the default framework, the authors try to detect human falls in a video. Our second objective is to study the applicability of this model on the parameter intrusion detection task. So, what is a parameter intrusion detection task? Before defining it, we must define what is an intrusion. We have an intrusion when one or more unauthorized objects move in a particular area during a certain time interval. In images below, objects in red bounding boxes are causing intrusion. Observe that some cars are not marked for intrusion. It is because they are stationary and hence do not cause an intrusion. So the PID task is to detect all frames containing intrusion in the video. Initially, PID task was addressed as a moving object detection task with the help of GMM and background suppression methods. But this approach disregards the fact that not all moving objects cause intrusion. The second family of methods use some image-based classification to classify the detected moving objects as intrusion or not. Some works have used HOG and handcrafted features with SVM and other classifiers. And recently, there have been a work which used CNN-based image classifier. But all these approaches have certain limitations. Instead of treating video as a spatio-temporal block, they treat its spatial and temporal dimensions independent of each other. Furthermore, all these approaches are supervised-based learning approaches. But we cannot apply supervised learning in real-life PID system because it is very difficult to have a large annotated dataset. This is due to the fact that intrusion is a rare event. So, we need an unsupervised learning approach which can jointly learn spatio-temporal features from the video and detect intrusion. As stated before, we use the approach of default framework for PID task. We have a window of fixed size that we slide temporally over the video. We input the frames of each window into a 3D convolutional autoencoder. The 3D convolutional autoencoder reconstructs the frame of the window. Given input frames and reconstructed frame, we calculate mean squared error loss and then we backpropagate it for training the model. The idea here is to train a 3D convolutional autoencoder on normal videos, meaning videos without any intrusion or fall. This is to learn what is normal. The hypothesis here is that during testing, intrusion frames of video will have higher reconstruction error and thus we can detect intrusion or fall frames. Here we represent spatio-temporal convolutional autoencoder, also called 3D convolutional autoencoder. The input is an 8-frame window. It is encoded by 3D convolution and 3D max pooling and decoded by 3D deconvolution, which gives the reconstructed window of same size. We test 3 variants here. The first 2 variants use 3D convolution and 3D max pooling for encoding. The first variant uses 3D upsampling and 3D convolution for decoding. The upsampling operation scales the input to higher dimension by nearest neighbor interpolation. The second variant uses 3D deconvolution for decoding. Deconvolution is a learning operation that transforms the input in opposite direction of convolution, that is from lower to higher dimension. And the last variant is C3D, as it is inspired from the C3D architecture of 3D CNN. Here 3D convolution is followed by either 2D max pooling or 3D max pooling for encoding. For decoding, either 2D upsampling or 3D upsampling is followed by 3D convolution. In all these approaches, 3D convolution is essential here as it learns spatio-temporal features jointly from the video. Finally, for training, we use ReLU activation function on hidden layer and 10H for output layer. We optimize the network with error delta optimizer and train for 500 epochs. We have a learned model now, and we want to detect abnormal events like intrusion or fall. Given a test video, we follow the same procedure of sliding window. For each window, our learned model reconstructs its frame. Given original and reconstructed frame, we obtain reconstruction error for the window. But each frame can appear on multiple windows, so we try to obtain reconstruction error for each frame. If reconstruction error of a frame is higher than some particular threshold, we mark it as an abnormal frame, that is, fall or intrusion. Here we can see 3 sliding windows and reconstruction error associated to each of them. Since a frame can have multiple reconstruction error, we need a way to obtain single reconstruction error for each frame. One way to do this is to obtain reconstruction error of a frame from the first window it appears in. So for the first frame, reconstruction error appears first time in the first window. For the second frame, also first window. Until 8 frames, reconstruction error appears first time in the first window. For 9th frame, it appears first time in the second window. For 10th frame, it appears first time in the third window, and so on. We call this type of per frame reconstruction error as reconstruction error R. Another way to obtain per frame reconstruction error is to calculate mean and standard deviation of the reconstruction errors across the temporal context. For example, here for the frame 3, we can obtain per frame reconstruction error from mean and standard deviation of these 3 reconstruction errors. This type of reconstruction error is called cross-window reconstruction error. Marking a frame as normal or abnormal depends on the threshold. To evaluate our model on different sensibilities and sensitivities and to be independent from the choice of threshold, we plot the ROC and PR curves. The area under these curves gives the overall performance score. For reproducibility, we use the publicly available thermal fall dataset. Here, for training, we have 9 non-fall videos, and for testing, we have 35 videos. Out of these 35 videos, only 2.19% are fall frames. Here we have a video demonstration for the fall detection task. As you can see, on the left we have the original image, on the middle we have the reconstructed frame, and on the right we have their associated error. As you can see, RA increased as soon as the person entered, and it exploded to a high value as soon as the person falls. Here are the reproduced results on the fall detection task. The first column shows the 3 model variants we described. We evaluate each model with the 3 per frame reconstruction errors. The third column shows the testing time. The fourth column is called AU-ROC per video. In this, we calculate the AU-ROC score for each video. Then for the whole test set, we perform mean of AU-ROC scores for all the videos. The value here represents mean AU-ROC score, and in brackets is its associated standard deviation. This is how they evaluate in the default framework. Comparing our reproduction, we can see that we correctly reproduce their results. The last 2 columns shows AUC all video score. Here, the AU-ROC or AUPR score for all the test video is calculated at once. This score helps in measuring how well the model can capture inter-video variabilities. This is the standard way to calculate AUC. We can observe that upsampling models have fastest and highest performance as compared to the other 2 models. Furthermore, models with R sigma perform superior to others. Overall, we can say that we have up to 6% degradation of AU-ROC scores from per video to all videos. More importantly, we have a very poor AUPR score. AUPR score is important here since it is sensible for highly imbalanced dataset, and fault detection is a highly imbalanced dataset with only 2.19% of all frames. So a bad AUPR score here means that the model is not correctly able to capture faults. For the PID task, we use our private single-view thermal dataset. With human, car, bike, truck, etc. as unauthorized classes, we train on 80 non-intrusion videos and test on 100 videos. This is the result demonstration for the PID task. The blue dashed line here represents a threshold. This threshold is just for the demonstration purpose and is chosen from the ROC curve when the TPR was highest and FPR was lowest. As you can see, as soon as the intrusion enters, we have a very high reconstruction error, and all the frames in red are intrusion frames and all the frames in green are non-intrusion frames. As soon as the intrusion leaves, we are back to the green frames. Here are the results on the PID task. As you can see, we only evaluate AUC all videos as it is the standard way. We can observe from the results that upsampling models are again the fastest and with the highest performance. We can also see here that models with R sigma again perform superior to others. Overall, we can see that we have small gap between AUROC and AUPR scores, and we have a good AUPR score. This means that this model is able to detect intrusions correctly. To conclude, we applied STCAE to two unsupervised tasks. On fault detection, we reproduced the results of the default framework. We observed upsampling models and models with R sigma performed superior to others. We also extended the evaluation with AUC all videos with captures inter-video variabilities. AUC per video in turn showed very optimistic view of the model. We found large gap between AUROC and AUPR scores with poor AUPR scores. This means that these models are not able to detect faults correctly. We applied these models to the PID task. We again found that upsampling models and models with R sigma performed superior. We had a small gap between AUROC and AUPR scores, and we had good AUPR scores. This shows that STCAE is suitable for the PID task. For future works, we would like to test our model robustness on different lighting conditions, intruder speed, and its distance from the camera. We would like to do cross-video testing, and we would like to work on adaptive threshold selection. Thank you for your attention.